So section 4.5 is about linear approximations. So linear means a straight line. So what's going to happen is we're going to have a graph, and it doesn't have to be a straight line, but as we zoom in closer and closer and closer, the graph is going to start to look more linear. And so this gives way to the fact that we can perform a linear approximation. So what we're going to do, the linear approximation is going to be represented by L of x. And to get that function, we are going to plug in some value a to the original function, plug in that same a value to the derivative of our function, and multiply that by x minus the a value. Okay, so let's go ahead and do an example. So here we want to perform a linear approximation to the function f of x when x equals 1, and we're going to use that to approximate the value of f at 1.1. So our function is f of x is the square root of x. So what I like to do is I like to rewrite that as x to the 1/2. Because it's just a little bit easier for me personally to take the derivative. So then the derivative is going to be 1/2 x to the negative 1/2, which I could write that as 1/2 times the square root of x. Okay. So in this case, my a value is 1. And so then I can write down the formula for the linear approximation. Okay, so f of a is me plugging in 1 to my original function. So in this case, that would be the square root of 1. So here I'm going to get 1. And this is me plugging in 1 to my derivative. So if I did that, I'm going to do that on the side here. That's going to give me 1/2. So plus 1/2 times x minus 1. Okay, so essentially what I can do is I can combine my like terms. Minus 1/2. And if I do 1 subtract 1/2, that's going to give me a positive 1/2. And if I wanted to make this just look a little bit nicer, what I could actually do is factor out a 1/2 since both of those terms have that, which would leave me with 1/2 times the quantity x plus 1. Okay. So that's the linear approximation to the square root of x. So now what I'm going to do is I'm going to use that to approximate the value of the square root of 1.1. And that is going to give me about 1.05. Okay. Now, if you actually type into your calculator the square root of 1.1, you're going to get about 1.048808, blah, 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 blah. So it does round to about 1.05. All right, so that's good. You always want to check to make sure that your approximation is sound, meaning it is very close to the original. Okay, so we're going to see an example where that does not happen next. Okay, so we're going to be using the same linear approximation formula for this next example. Okay, so I'm just going to rewrite the original here. So we had lmx equals 1/2 x plus 1. Okay, so let's go ahead and plug that in. All right, so when I do that, I am going to get 0.55. Okay, so we need to check. So in this case, the square root of 0.01 is about 0.3162. Okay, so that is way off from our 0.55. Okay, so what we need to do is we need to try to find an A value that is really close to 0.01. And I'm getting 0.01 from here. So let me write that down with a text. So we need an A value that is very close to 1. Okay, so I'm going to pick 0.09. So I'm picking okay. So I'm getting 0.09 because I know that 0.01 is the same as, like, for instance, 10 out of 100. If I were to convert that. So I'm picking 9 out of 100. Now, you're probably asking yourself, how did you know to pick that? It just comes from practice. So I picked something that was really close to it. So it's just, you get used to what you need to pick. Okay, so we're going to have to redo this using this A. So my formula, remember, okay, so when we plug in our A, so we're going to get the square root of 9 over 100. Okay, my derivative of that is going to be this. And my x value is 1/10. And my A value is 9 over 100. Okay. So we're getting about 19 over 60, and if you type that into your calculator to get the corresponding decimal, you will get 3162, which is much closer to the true value, okay? So it's always important that you check these to make sure that you are getting a value close to the true value. Otherwise, the approximation is off and you need to reevaluate what you've done. Okay, so let's do another kind of different example. So in this case, we want to do the linear approximation of f of x equals sine x when x is 0. And then we're going to use that to find a sine of 2.5 degrees. Okay, so first, you know me, I like to write down my formula. So okay, so the first thing that I need is I need f of a, which in this case is sine at 0. And if you remember, or you look at your unit circle, that's going to be 0. Now, the derivative of sine is cosine. So cosine at 0 is 1. All right, so now I've got my pieces to plug into my formula. So f of a was 0. F prime of a was 1 times x minus 0. So that's giving me a linear approximation of x. Okay. All right, so now we can perform our approximation of sine at 2.5 degrees, but first we need to convert that 2.5 degrees to radians. Okay, so 2.5 degrees, what we can do is we know that we have 180 degrees, and that is equal to pi. And so if you perform the math, you're going to get pi over 72 radians. Okay. So we can just substitute that in now to my linear approximation, and we will get pi over 72, which is about 0.0436 radians. Okay. And you can also check that to verify that it is true. Okay, let's learn another rule. Okay, so in this case, we are going to talk about the relationship between the change in x and the change in y. Okay, so this triangle means delta, which refers to change. No, get that going. All right. So the reason why this works is if I were to take my original function that I had, f of x is approximately equal to f of a plus f prime a times x minus a, right? So what I could do is I could subtract over the f of a. So we could say f, of x minus f of a is approximately equal to f prime of a times x minus a, right? And so essentially, this right here refers to my change in y. This right here is referring to my change in x. So we can say that the change in y is approximately equal to the derivative of f with respect to, with a plugged in, multiplied by your change in x. And the reason why this works is because a change in y, the function value, can be approximated by the corresponding change in x, magnified or diminished by a factor of f prime of a. So f prime of a, the derivative, is the rate of change of y with respect to x, okay? So it's really all coming full circle. So let's go ahead and knock this out with an example. So we are going to approximate the change in y, which equals f of x, and the function is x to the 9th minus 2x plus 1, as x changes from 1 to 1.05. Okay, so let's find the derivative. And that is equal to 9x to the 8th minus 2. Okay. All right, now we need to figure out what the change in x is. So you're always going to use the second value and subtract the first value from it, because you need to make note if it's getting bigger or smaller. Okay, so my change in x is 0.05. All right, and in this case, my a is 1, because that's where my x started. I know that from here. So now I'm just going to substitute everything in. So my change in y is approximately equal to f prime a times my change in x. Okay, so if we were to plug in 1, we would get 9 times 1 to the 8th minus 2. In this case, that would be 7. So change in y is approximately equal to 7 times 0.05, which is about 0.35. So my change in y is approximately equal to 0.35. All right, let's do another one. Approximate the change in the surface area of a spherical hot air balloon when the radius decreases from 4 to 3.9. Okay, so the formula for surface area of a sphere is 4 pi r squared. I'm going to take the derivative of that. So the derivative of my area is going to equal 8 pi r. I am starting with a value of 4, so my a is going to be 4. And I need to find my change in my radius. And so to do that, I'm going to subtract 3.9 meters minus 4 meters, which is going to give me negative 0.1 meters. All right, so let's just plug in 4 for this. So if I do that, I'm going to get 8 pi times 4, which is 32 pi. And now I have everything I need to plug in. So I'm going to write this in terms of S for surface area and R for radius. So my change in S is approximately equal to the derivative of my surface area with my A value plugged in times my change in my radius. So that means that I am going to plug in 32 pi and negative 0.1 here. And that is going to give me that my change in S is approximately negative 10.05 meters squared. All right, so there are two formulas that you can use for this function. If you are trying to approximate the function value near some value, then you're going to use the first one that we learned. And if you're trying to approximate the change in y, you're going to use the second formula. Okay. Okay, so if f is a differentiable function on some interval that contains x, a small change in x is denoted by the differential dx. The corresponding change in f is approximated by the differential dy, and dy is going to be equal to the derivative of the function with respect to x dx. Okay, so this is going to look a lot like that implicit differentiation that we did back in chapter 3. All right, so we're going to use the same notation. So we're going to say that dy is equal to f prime of x dx. So the first thing that I'm going to do is I'm going to find the derivative of f of x. Okay, so I'm going to rewrite my function to say 3 cosine x times cosine. This just helps remind me that I need to do the product rule. Okay, so the derivative of cosine is negative sine. So essentially when we're doing our derivative with our product rule, we're going to end up with negative 3 cosine x sine x and plus okay. So if I were to simplify that, I would end up with negative 6 cosine x sine x. Okay, so we can actually simplify this using the double angle identity. So this is a throwback to pre-calc. Okay, so your double angle identity, what this is telling you is the sine of 2x is equal to 2 sine x cosine x. Okay, so using that, I can simplify that because I've got a sine x cosine x here. So all I need to do is divide this negative 6 by 2 to get what is going to be left over in front of my sine 2x. So in this case, it's going to be negative 3. So we simplify this to be negative 3 sine 2x. Okay. So if you didn't remember the double angle identity, there's a bunch of different simplifying rules in the front of your textbook that you can reference. So don't feel bad if you did not remember that. All right, so now all we have to write down is we're going to say the change in y, dy, is going to be equal to negative 3 sine 2x dx. And then we're all done. Okay? All right, let's do one more example. All right, so we're going to do this one, and hopefully you are noticing we're going to need to do the chain rule. All right, so I could rewrite this as x squared plus 1 to the 1/2, right? So what that would tell me was my u would be x squared plus 1. The derivative of u would be 2x. And then u to the 1/2 power. When I did my derivative, I would get 1/2 u to the negative 1/2. And so to simplify, I would end up doing times du. So in this case, it would be 1/2 x squared plus 1 to the negative 1/2 times 2x. Okay, so I'm going to rewrite that. So we would end up with 2x in the numerator over 2x squared plus 1 to the 1/2 in the denominator. And the 2's would essentially cancel out in the front there. And you could also write this as the square root in the denominator as well. And that's what I'm actually going to do when I substitute it in. Okay, so remember we're doing dy f prime x dx. So dy equals x over the square root of x squared plus 1 dx. And then that's it, all done.